x cubed plus 1 over x minus 2. This is a little bit of an unusual question, because if you let u be x cubed plus 1, its derivative would be 3x squared dx, and there is no x squared dx on the top, right? So this is not your typical u-substitution question. Again, this is a new one. I don't expect you to get it, but just out of curiosity, does anyone have any suggestions what we could do here? Several. Yes, Ryan? That's an interesting. Solve for x. We can do it that way. It's still going to be really long, but at least it's a way to do it. The suggestion is that u be x minus 2, right? Then x would be like u plus 2, and then you could put that under that x cubed. It would be like u plus 2 to the cube, but you still have to expand that cubic expression. It's going to be still very long, okay? Any other thoughts? Again, we haven't seen one like that. I don't expect you to get it, but just kind of pushing our brain and, just to think a little bit creatively. Yes? Devin, maybe a suggestion? Okay, well, yes, I heard someone say quotient rule, but we don't really have a quotient rule for integration, but we can divide these two polynomials, because if the degree at the top is equal or higher on the top than it is on the bottom, you can always do either synthetic division or long division. Then you're going to have like a polynomial plus a quotient plus a remainder over divisor, I should say. And then you can see what we can do at that point. We can worry about it when we get there. So at the moment, let's begin with this idea that when the degree at the top is higher than the bottom or equal to the bottom, that you can actually do a long division first, and this will help us with the process. I'm going to do x cubed plus 1 divided by x minus 2. Now let's see, x goes into x cubed how many times? X squared times. So x squared times x is x cubed. X squared times negative 2 is negative 2x squared. Now I'm going to subtract. So I change the signs and I add. The x cubes are going to cancel. I have 2x squared and bring down the 1. Okay, next question. X goes into 2x squared how many times? 2x times. So 2x times x is 2x squared. What else should I be writing down here? Whatever you write on the top, it should be multiplied with the entire divisor. So far you multiplied it by x, also multiply it by negative 2. So what is 2x times negative 2? Negative 4x. Again, change the signs and add. So this becomes negative, positive. Now add the two rows. So we have 0x squared plus 4x plus 1. So we're going to ask one more time. Does x go into 4x? Okay, so how many times? 4 times, right? So I'm going to put 4 up here. 4 times x is 4x. 4 times negative 2 is negative 8. Change the signs and add. The 4x's cancel. I'm left with a 9. Does x go into 9? No, finally we can stop, right? When the degree of your remainder is less than the degree of the divisor, then you can stop. So what we're saying is this question can also be written as follows. The quotient plus 9 over x minus 2. Does this look any easier to integrate than the original one did? It does, because we have this nice rule about sum or difference of it. When you're integrating, you can distribute the integral over a sum. So you can go one piece at a time. And what are we going to do when we get to the last one, that 9 over x minus 2? We can do a u-substitution there, right? So let's finish this one up. I'm going to just continue down below. The integral equals, integrate the x squared, and what do you get? x to the 3 over 3. Integrate to 2x, and what do we get? X squared over 2. Actually, 2x squared over 2, and those 2's are actually going to cancel. It's going to be x squared. Okay. Integrate to 4, and what do we get? 4x. Again, basically, I'm going like line by line, item by item, anti-differentiating each one at a time, right? And now we're at the last one. There we're going to do a quick u-substitution. Let u be equal to x minus 2. Then du is 1 dx, right? And that integral can be written as 9 over u. Instead of dx, I will put du. So what will be the answer there? 9 times natural log of the absolute value of u plus c. So I'm going to copy that down then. So the last term there is integrated as 9 times natural log of x minus 2 in absolute values plus c. If I had limits of integration, this is where I would plug them in for x. And in this question, that would be really the best place because you already had some x's there and you have some u there, but you would not be able to have everything in terms of u's. So for this question, the best way to substitute would be in this last step when everything is back in terms of x. Now, I want you to look at this term once again and tell me if you could have if you have guessed what the answer would be from now on without doing a u sub. If you have 9 over x minus 2, the answer turned out to be 9 times ln absolute value x minus 2. This will occur if du equals dx, like if you have like x minus 2 or x plus 3, something like that. But if you had like 2x minus 1, you couldn't jump to such a quick conclusion. You have to do a little u substitution there. But it's good to recognize sometimes these easier cases. Like if du is exactly dx, then you can kind of avoid that u substitution step and jump to the conclusion there. If you don't feel comfortable doing that, by all means show the work. You know, that's always safer. But it's also, as you move forward, you know, into the PQ, etc., it's good to be quick at doing some of these things. But you have a lot of time to get there, so don't worry. All right, another example. Any questions on this one? So if the degree of the top is higher, we're going to do long division, right? Even when it's equal, like if you have like x plus 2 over x minus 1, you could still do long division there. That will still work, okay? All right, let's try another one. Okay, let's try the one on the top. Okay, let's take a look at the solution. I'm going to let u be 1 minus 4 cosine theta. So du is, okay, derivative of cosine is negative sine, right? But there's another negative sitting in front, so it's going to turn out to be positive, the end result. So it's going to be plus 4 sine theta, d theta. So when I go back to this integral, I'm going to hold off on the limits for now. The bottom is what we call u. And luckily, the top is exactly as what? Du, right? 4 sine theta d theta, that's exactly the same as du. I don't have to solve for anything. It's right there in front of me. And what is the integral of 1 over u? ln of the absolute value of u. Here, the absolute value will prove to be helpful as when you go to the substitution of the limits. But let's bring in the original variable. Going from 0 to pi over 3. Okay, I'm going to start by plugging the upper limit. What do we know about cosine of pi over 3? Pi over 3 is 60 degrees. Cosine 60 is the same as sine 30, which is what? 1/2, right? That's one of the important angles we should know. So this will be 1/2 minus ln of 1 minus 4 cosine of 0, which is What is cosine 0? 1. Okay, simplifying the first expression, we have 1 minus 2 under the absolute value signs, because 2 goes into 4 2 times. And that's like negative 1, except it's going to come out as ln of positive 1 in the next step, right? And then the other part, ln of 1 minus 4, that's ln of negative 3. That'll come out, because this absolute value takes, absolute value gives you the positive quantity of anything inside it. So that'll be like ln of 3. Because absolute value of negative 3 is positive 3. Now, what do we know about ln of 1? ln of 1 is 0. So what we have here, we have 0 minus ln 3. So one way to leave the answer is to say it's negative 1 times ln of 3. Another way to give the answer is on the calculator. Just a negative ln 3, and you get negative 1.098, roughly negative 1.1, let's say. And there is one more way to leave the answer, and sometimes the book will do that and it will confuse the students a lot, but it shouldn't. They will leave the answer like this, ln of 1/3. Can anybody explain how they're doing that? How come negative ln 3 is the same thing as ln of 1/3? Yes, how do you combine them? Basically, this negative can go up to the power, right? That's one way to look at it. So you can do like ln 1 minus ln 3. You're doing like ln of the quotient, ln of 1/3. You can do it with that idea. You can certainly do that. Like at this step, Madeline's suggestion, if you're subtracting two logs, it's log of the product. It's a good rule to review. This is the same as ln of 1/3. That's one way to do it, right? And what's another way to do it? If you have negative ln 3, this negative 1 can be written on the power, 3 to the minus 1. Remember that rule? That if you have a number in front of ln, you can put it on the top as a power, remember? So now what is 3 to the minus 1? 1/3. So once again, the answer is ln of 1/3. So you can leave it like that, or any one of the ways we discussed, obviously, would be acceptable. Okay, let me see which other question I want to do. I'm going to do one more example, but before I do that, I want to give you some tips about what would you do if you have different bases. Like so far, we always emphasize base e, like e to the x or ln, which really represents logarithm base e. What if you had a different base? So for example, what if you were trying to integrate something like 2 to the x dx? First, let me give you the shortcut answer, and then I'll try to explain that to you. The shortcut answer is, in a way, this is similar to e to the x. What was the antiderivative of e to the x? Itself, right? E to the x. So you might say this will be also itself, 2 to the x, except that there's an extra coefficient. You have to divide it by ln of the base, ln of 2. Like if it was 3 to the x, you would divide it by ln 3. If it's a to the x, you divide by ln a. And what is happening with e to the x? Why is that not showing up? Because if you divide by ln e, what happens? Exactly, ln e is 1. So we don't even see that coefficient being there. And we get just e to the x. So this is why the base e is like, it's called the natural base. It's used so often because it's the one number that makes that coefficient disappear, and you end up with the easiest base to work with. You don't have these extra numbers hanging around when you do an integral or a derivative. Now, why is this rule working the way it is? I'm going to try to show you an explanation of that. So let's try to rewrite 2 to the x. This you may want to just watch, just perhaps write this as a rule, but what I'm about to do, I just would rather you concentrate on the understanding of it and don't worry about writing it. So I can rewrite 2 to the x as follows. I can write it as e to the ln of 2 to the x. Let me know if you agree with this. 2 to the x is the same thing as e to the ln of 2 to the x. How do I know that? Because doesn't e to the ln cancel each other? And you get back what you started with. So really the right-hand side is really 2 to the x, and the left-hand side is 2 to the x. The reason I wrote it that way is because I know the rule for e to a power. I can apply that rule. But before I do that, I'm going to bring the x down. This x, can I write it like this? Because like if you have like, let's say, ln of x to the 5, you can bring the 5, you can write as 5 times ln x, right? Whatever the constant is, it can come down. So here you have ln of 2 to the x can come down. Okay, now this looks exactly like to me something like, let's say, e to the 5x. How do you integrate e to the 5x? E to the 5x divided by the constant 5, right? Here, what is the constant here? The constant is ln 2. Think of it as like e to the ln 2 times x. Your 5 there is your ln 2 here. So what will the answer be? The answer will be e to the same power divided by e to the ln 2 times x divided by what? Whatever that constant is, and that constant in this case happens to be ln of 2. And if you don't see this as the answer I gave you earlier, put this back again. Put this x back in the power. So you have e to the ln of 2 to the x. And what was e to the ln of 2 to the x? That's the same as 2 to the x, right? Because e to the ln cancels, and you do indeed end up with 2 to the x divided by ln 2 plus c. You can see, I mean, the derivation you don't have to do every day. You can just see it one time, why it works, and then you never have to do it again. But the rule that we have over here for you, occasionally you may need to know this rule. I'm not going to have you memorize this because I just don't think it occurs frequently enough for me to ask you to reserve it like a memory space location in your brain for this one. I don't think it's worth the memory space. It doesn't come up very often, but every once in a while you may see it. All I ask is, if you see something like that, at least be able to find, where it is in the book, near where you did like derivatives of exponential functions or integrals of exponential functions, and just know that there is an answer and be able to find it. And if I ask you a question about it, I would first state the rule. I would say like integral of, let's say, a to the x is a to the x divided by ln a, and then I may ask you really something about that. But like I said, the most commonly used bases are the base e for the logarithmic and the exponential functions, and that's what we're going to be using here as well. All right. So with that, I think I'm going to be sending you guys to your groups. But the first question I ask you to do actually, not the first, but one of the questions I'm going to ask you to work in your groups today is going to be this one. Integral of x over x plus 2, and the limits are from 0 to 4.